should automatically turn on, don't you think? Maybe it's not convenient, but there should be a setting at least to enable automatic turning on. Okay. Yeah, as I said, we're going to have another research lecture today covering prefetching, reinforcement learning based mechanisms for data placement in solid state drives and more in-memory acceleration of genome analysis. But before we start, I'd like to announce the exam date. Now you have a choice. So there are two options, and I'd like to get a vote before we decide. Your vote will inform the decision. One is December 22nd, which gives you enough time to prepare, and the other is December 16th. Okay, who votes for December 16th, let's say? I don't see any hands. Of course, only vote if you're taking the class. I can tell also. Who votes for December 22nd? Okay, looks like that's a clear winner, at least among the people who are here, right? Yeah. So yeah, we'll have the exam then on December 22nd in classroom during lecture. We will release a bunch of material for you to study. I mean, the exam is not going to be any surprise. It's only 30% of your grade. It's not that much, so you don't need to worry too much about it. As I said, my goal in this course is for you to learn as opposed to worrying too much about grades. Hopefully you learned a lot so far on computer architecture, and hopefully you will learn a lot more. But the exam we will release, certainly the homework material is useful for the exam, but we will also release some solutions to past questions. We may even have some discussion sessions. These will be online, you can watch at your convenience. But we may also, feel free to also use the office hours. We can also potentially have a discussion session where we interact. So that's the exam. That's out of the way. And then there will be two other labs. One is prefetching and the other is multi-core and cache coherence, but they're both going to be bonus labs. So again, hopefully you will do them so that you can learn. But essentially, you can also do them to compensate for some other loss that you may have had in other part of the semester, right? Potentially in the exam or other homeworks. So keep that in mind. These two labs are quite nice, actually. You've done labs on very interesting things, clearly. Caching, memory hierarchy, memory scheduling, and processing in memory architectures. So that's, I believe, the first lab ever in the world about processing in memory. That's my thinking. I have not heard of anybody even covering this topic as much in general. So you're really at the cutting edge, basically. But we're also learning a lot of fundamentals, as you can see in this course, right? So it's not just cutting edge research, it's a lot of fundamentals. And we're going to see even more soon. So my hope is that you will actually do the labs and learn, because the prefetching lab is fun. Multi-core and cache coherence lab is probably the hardest lab you will do. Not the multi-core part, cache coherence lab part, to get it working. But it's a good challenge also. It's good to do that. So it's 6 labs, basically. Just to put it in context, when I taught this course at CMU, there were 8 labs. And none of them were optional. Yeah. So think about your competition, basically. Yeah, it's good to have a worldwide view, let's say. I think the semesters are a bit shorter here, and yeah, I don't know. Okay, any questions on these so far? Yes. Yeah. I think maybe Mohammed is the right person to answer that. I don't know if you announced it, but
end of January.
Yeah. Yeah, but if you want to get feedback, do them earlier. End of January, then you will probably not get a lot of feedback. Yeah. Okay, any other questions? Okay, and then there will be 2 other homeworks. They will be released, but in homeworks, you know that a lot of bonus questions exist already. So basically, my hope is that you will learn a lot and not worry too much about your grade, because there are a lot of opportunities to get a 6.0 in this course, really. Okay, any questions? No? Then what we will do is we will start with the research lectures. Maybe Rahul, you can come and start sharing it. There should be a Zoom screen that you can get into. Yeah, Rahul. So we will have again 4 cutting-edge research topics. 2 of these are things that I have talked about. Well, the first one is going to be presented by Rahul, who is a PhD student in my group. He's going to talk about Pythia, which is the reinforcement learning-based prefetcher. And then he's going to talk about Hermes, which is a perceptron-based off-chip load predictor, so that you can actually decide whether a load is going off-chip and start the request early. And this first work was published at ISCA in 2021. The second work was published at Micro 2022. And yeah, we'll discuss. So feel free to ask questions. We'll have 2 more after that, but I'll introduce them when the time comes. Yeah, this is a good opportunity to ask a lot of questions. And Rahul is waiting for them, right? Okay.
Thanks, Onur. Hopefully this works. Is it working? Hello, it's working, right? Okay. Give me 1 sec. Is it working? Okay, perfect. So yeah, hi everyone. I'm Rahul. I'm a 4th-year PhD student working with Professor Onur Mutlu in Safari Research Group. So today we are going to discuss 2 works, right? As Professor Mutlu also mentioned. So the first work and kind of the first work and the second work are kind of synergistic to each other. So let's see what they mean. So the first work is called Pythia, Customizable Hardware Prefetching Framework using online reinforcement learning. So I mean, I guess this is pretty much evident by this time at the lecture that, memory latency is a huge problem in today's high performance computer architecture, right? So, and we have seen this graph before in the past few lectures that, in the last couple of decades, we have seen an enormous growth in the main memory capacity as well as the bandwidth, but the latency is not pacing at the same pace of the capacity and the bandwidth that we are seeing. So, this like slower main memory is creating a problem in today's high performance processors, and especially for executing workloads that exercise huge data footprint, like for example in memory databases, large scale graph analytics, data center workloads, and so on and so forth. So, like architects have traditionally, relied on these 4 key principles to alleviate the latency challenges stemming from the like the slower main memory, out of order execution, multi-threaded processing, caching, and prefetching. So for the first lecture, we are going to focus on the prefetching part. In the next few in the next lecture, we are going to focus on prefetching as well as caching together. Okay. So yeah, so just to give you a brief, recap of what prefetching is. I mean, we are covering this from the last two lectures, I guess. So I'm just going to, flow quickly. So the idea of prefetching is, to fetch the data before it's actually needed. Hence the name comes from prefetch, right? Why do we need to prefetch? Because memory latency is high, as I'm saying. And so if we can prefetch accurately as well as early enough into the program execution, we can hopefully reduce or completely eliminate the latency of fetching the data from the main memory. Now, so prefetching clearly involves in predicting which addresses the program is going to demand next, right? So this prediction of the address is pretty, let's say it's relatively easy if the workload has some sort of regular access pattern. So you can mine some sort of, let's say, predictive pattern mining from the program addresses. But if the workload is kind of the address pattern is much more irregular or let's say random, then the prefetcher might actually mispredict a lot based on what the program is going to demand next. So we evaluate a prefetcher in 4 traditional key metrics: the coverage, accuracy, and timeliness. And we are going to come to the later matrix later. So the coverage is defined as the ratio between used prefetch divided by the total number of demanded memory access from the core. So it's essentially giving you a feedback of how much, let's say, demand request you are actually correctly predicting, right? So the higher is the better. The accuracy is defined as the ratio between used prefetch and the send prefetch. So it's basically giving you a feedback that, okay, how accurate your decisions are, right? Again, the higher the better. The timeliness is defined as memory access latency saved by a prefetch request. Again, higher is the better. But apart from these 3 metrics, right, so we have other metrics also which we are not just equal, but also probably even like equally important for comparing a prefetcher. So they're like bandwidth consumption, cache pollution, energy consumptions, and many more basically. So we're going to look at the entire picture of how to design a good prefetcher, not only in terms of, let's say, coverage and accuracy, but also some of the, let's say, system level analysis, let's say bandwidth consumption and cache pollution in this lecture. Okay. So prefetching essentially involves in, answering these three questions: what we want to prefetch, when we want to prefetch, and how we were going to, let's say, predict that this request is going to be demanded next by the processor. So for the sake of this lecture, we are going to focus on the how part. So let's first try to understand, like, let's say, how the traditional prefetchers work, right? So there are broadly three classes of prefetching techniques. So software prefetching, where the programmer or the compiler itself tries to insert prefetch instructions. So hardware does not understand. It's basically, the programmer itself is inserting explicit instructions. The execution-based prefetches, which we have covered in the last lecture, the run-ahead execution is a good example, where the thread is some sort of, let's say, program context is executed to prefetch the data of the main program. And then the hardware prefetching, where the hardware itself is learning patterns from the program accesses. I mean, though execution-based prefetcher is kind of a class of the hardware prefetcher itself, but I just put it in a different way because it doesn't try to understand, let's say, the pattern. So
it's not necessarily a class of hardware prefetching. There could be software-based.
Software prefetching also, yeah. Yeah. Okay, so maybe then it's better to have it as a individual class also.
Absolutely better to have it as an individual.
Okay. So hardware-based prefetching essentially, focuses completely on hardware monitors to, understand what is the pattern in the memory accesses that the program is generating, and based on that pattern mining, we prefetch or let's say predict which load request, which address is going to be demanded by the processor next. Okay, so this work that we are going to discuss, Pythia, is based on the hardware prefetching class. So we are going to discuss how it's actually learning, and let's say the matrix that we have discussed before, right? The coverage, accuracy, and the system bandwidth. How they're making use of those system level feedbacks to make better prefetch decisions. Okay, so yeah. Hardware prefetching. So I'm giving you brief examples of how hardware prefetching, let's say, works, right? So I mean, we have seen these examples in last lecture, I guess. So I'm just going a brief run through. So this is one example where, let's say, this program counter, right? So the PCX is trying to load these addresses. So these are the cache line address: A plus D, A plus 2D, A plus 3D. So you can clearly see that whenever PCX is trying to access a address, it has a constant delta between the previous access that it has seen. So there is a constant delta of D, right? So we can learn this type of access pattern, and we can use this for predicting, in a sense that, okay, if PCX is accessing cache line B, then we are going to predict that, okay, B plus D is going to be demanded next. Okay. So another example can be, let's say, this is the access pattern that we are seeing from the program. So the cache lines are accessed like A plus 3, A plus 5, A plus 8, so on and so forth. So what you can see that if you look into the cache line delta, right? So delta in the sense that it's between two consecutive cache line accesses, right? So you're seeing the cache line delta of plus 3 and plus 2 are repeating alternatively. So whenever you're seeing plus 3 first, and then plus 2, plus 3, plus 2, and so on and so forth. So you can use and exploit this learning, saying that, okay, if I see plus 3 as the last delta, so then my processor is going to probably demand the next cache line, which is 2 delta ahead. Similarly, if I have seen 2 in the last delta, we are going to demand 3 delta ahead. Okay, so what essentially it's happening here is that we're using some sort of let's say program context information, right? In this case, it's a program counter. This case, this is the cache line delta to extract some sort of let's say patterns from these memory accesses. So we're calling this program context information that we are using for extracting information as the program features. So these are the program features which are essentially giving you some sort of understanding of how the pattern is getting mined from the execution. So what a prefetcher essentially does is it associates a program access pattern with this sort of program feature information and learns this correlation basically that, okay, whenever this feature repeats, that access pattern is going to repeat again. So in the last example, whenever the PC repeats, the same delta would repeat. Whenever, let's say, the last delta is +3, it repeats again, probably your next delta is going to be +2. So that's the correlation that the prefetcher is trying to learn. Okay, so some other examples of features can be, let's say, branch PCs, page number, page offsets, and any combinations of these attributes. Okay, so with this background in mind, now let's go to this walk, which is Pythia, a customizable hardware prefetching framework using online reinforcement learning. So let's jump into the executive summary of the work. So as I say, prefetcher is essentially a predictive, a speculative technique that predicts addresses of the future memory request by associating access patterns with some program context information, which we call program feature that I just mentioned before. So now we observe 3 key shortcomings in prior prefetchers, mainly that they use only single program feature when it comes to making this prediction. That's one. The second observation is that most of the prefetchers, they lack any inherent system level awareness, like memory bandwidth consumption, or let's say cache pollutions inherently inbuilt into that prefetching algorithm. And then they lack in silicon customizability. So to alleviate these challenges, the goal of this work is to design a prefetching framework that learns from multiple program feature as well as inherent system level feedback information. And it can also be customized in silicon. Even after, let's say, you fabricate this to a processor, you have the customizability to change the program feature as well as the prefetching objectives on the fly. So towards this, we propose Pythia, which is a hardware prefetching framework that formulates prefetching as a reinforcement learning problem. So Pythia can take adaptive prefetch decisions using multiple program features as well as system level feedback into consideration. Pythia can be customized in silicon for targeted workloads via simple configuration registers. I'm going to show you next. And Pythia proposes a realistic and practical implementation to implement reinforcement learning in hardware with much lower storage overhead as well as latency overhead. Okay, so we have evaluated Pythia extensively across a wide range of workloads, and we're going to show that Pythia works decently well as compared to prior state-of-the-art prefetchers in multiple bandwidth constraint as well as single core multi-core core configurations. And Pythia is completely open source. Maybe you can also think of using this infrastructure for your prefetching the prefetching lab also, and then just essentially play around with the code, and basically it works out of the box. Okay. So this is going to be the outline of today's lecture. So let's start with the going deep into the shortcomings of the prefetcher itself. So as I said, there are 3 key shortcomings that we are going to target in this work. So first, they mainly use only one program feature when it comes to learning the program patterns. Second, they lack inherent system awareness, and third, they lack in silicon customizability. So what does these 3 things mean? Let's go into a bit deeper. So the very fact that many prior prefetchers only use single program context information when it comes to learning the program pattern, they normally provide huge performance benefit when the pattern to the feature to pattern correlation exists. But if the feature to pattern correlation doesn't exist, then they fail. They fall short in providing performance benefit. So to illustrate this, I'm showing here 4 workloads on the x-axis. The performance from the no prefetching baseline on the y-axis, and for each workload we are seeing 2 prior prefetchers, SPP and Bingo, and Pythia which is our contribution, right? So the key takeaway, the key observation that I want to focus is that there are certain class of workloads, for example, Sphinx, Parsec, where Bingo as a prefetcher, which is proposed in early 2019, I guess. So Bingo, exactly, over 2019. So Bingo actually performs better than SPP as a prior based performing prefetcher. Why is that the case? Because the feature that Bingo uses, these type of workloads are actually the good candidates where the feature to pattern correlation dominantly exists. So as a result, you see a decent performance improvement over the prior based performing prefetcher SPP in this case. But there are other classes of workloads also, for example, James FTTD, where SPP simply outperforms Bingo. Why? Because the feature that SPP uses they are dominantly present in that workloads. So what this basically says, it basically says that if we only focus on one type of program feature when it comes to learning the program access pattern, we actually leave a decent performance improvement on the table. Instead of doing only one program feature, we just need to understand access pattern mining from multiple program features, not only relying on only one access program feature. Okay, so the second key, the key observation is that many prior prefetches. Do we have any questions till now? Okay, so the second key observation is that many prior prefetches, they basically have less understanding of their undesirable effects on the system. What do we mean by undesirable effects? Let's say, for example, memory bandwidth usage, cache pollution. And when I say they have a lack of understanding, means the algorithm itself has a lack of understanding. So there are works which we have covered in the past lectures that are for example, feedback directed prefetching, right? So which takes any prefetching algorithm as is, and then tries to implement these feedbacks on top of it. But then there are very less algorithms, even next to none algorithms basically, which has this inherent behavior of learning the inside the algorithm that consists of this program level system level feedback inbuilt into the algorithm itself. Okay, and now the question is like, if we completely disregard of those feedbacks, right? So we normally see performance loss in many resource constant configurations. So let me give you an example of that behavior. So again, we are going to show, I'm going to show, two workloads, the Ligra CC and the Parsec Canil. So in this left-hand chart, you're seeing the coverage, uncovered, and the over-predicted value from the prefetcher, right? So green, you can think of as a good one. White bar is basically, which is loss of opportunity. Basically, you want the green bar to be going 100% as possible, and you also want the red bar to be as low as possible. That's the holy grail basically. And on the right hand side, we are seeing for the same workloads and the same prefetchers, we are seeing the performance improvement on top of the no prefetching baseline. Okay, so the key takeaway from here, the key observation, and I want you to focus on let's say Bingo's performance improvement on these two workloads. So what we are seeing here is that, in Ligra CC and Parsec Canil, Bingo has almost similar coverage. So it's essentially saying that similar amount of main memory requests that these programs are making are actually successfully predicted by the prefetcher. But then in Ligra CC, we are seeing much lower over predictions also. I mean, these numbers by absolutely is huge, but still, in relatively these numbers, the Ligra CC, we are making less over prediction than the Parsec Canil workload, right? But then when it comes to performance, we see that even Ligra CC, it has lower over prediction, similar coverage, but the performance tanks even below the baseline, no prefetching baseline. Now, why that's the case? Parsec, even having a higher over prediction, it still improves performance, and it's not like it improves performance more than 6%, right? So why is that the case? The reason is, if we focus on Ligra's bandwidth consumption, the main memory bandwidth consumption, even without prefetching, it consumes a lot of main memory bandwidth. So what happens in this case is that even if you have a few over prediction, that also saturates your bandwidth, that also bombards the bandwidth consumption so much that your performance actually tanks, and you won't even get any good benefit of prefetching this part also. So what it essentially says that prefetchers often lose performance benefit due to the lack of system awareness, and we want to design a prefetcher that has this awareness already like inbuilt to the algorithm itself, and that's what we are going to show, like how Pythia is going to achieve this. And the third problem that we have seen is that all these prior prefetchers, like literally every prior prefetchers, they have statically selected the features that they want to exploit at design time. And after they have selected these features, they have designed a hardware based on exploiting those features explicitly. And yeah, so as a result, what happens is that you get a rigid hardware that only knows how to exploit and how to learn from that specific program feature. And if you want to change anything in the silicon, let's say I want to say that, okay, fine, I want to use some other program feature for mining patterns, right? You cannot do this. So the easiest way to do is to design a complete new prefetcher from scratch. You have to then extensively verify that design. Then you have to finally fabricate. And guess what? If you want to design a new prefetcher again in the future, you have to do this cycle, VCS cycle again and again. So this wastes a huge amount of research usage as well as human resource, right? So what we're going to so our goal of this work, right, is to alleviate these three challenges that we are mentioning. So the goal is twofold. First, we want to autonomously learn to what to prefetch using multiple program context information as well as system level feedback. And we want to have a framework that can be customized in silicon to decide which program feature, which program context information that we are going to use, or let's say what prefetching objective we are going to use on the fly. And towards this, we propose Pythia. And as I say, Pythia's the key idea behind Pythia is to formulate prefetching as a reinforcement learning problem. So now let me give you a brief example of a brief rundown of what reinforcement learning is, and then let's see how Pythia implements prefetching as a reinforcement learning problem. Okay. Do we have any question till now? I guess not. Okay. So let's move in. So reinforcement learning, it's basically an algorithmic approach to learn to take an action in a given situation to maximize a numerical reward. And every reinforcement learning framework essentially has two key components, the agent and the environment. The agent senses the state of the environment at every discrete time step. And given the state, agent takes some action. For every taken action, the agent receives a reward from the environment, which the agent uses to learn the correlation between how to take an action given a particular state. Okay. So now agent stores something what we call Q value for every state action pair, which represents expected reward for taking an action in that given state. So now what the agent simply does is that whenever it senses a state, it looks into the Q value table, or let's say it computes the Q value for that state action pair and selects the action that has the highest Q value for that given state. Okay. So now Pythia essentially takes that same framework that we are mentioning here and molds it into prefetching problem. So in Pythia's idea, the prefetcher itself acts as the agent, the reinforcement learning agent, and the processor and the memory subsystem acts as its environment. For every demand request that the processor makes, Pythia extracts a state of program feature from that demand request that it uses as a state information. And given that state information, it decides a prefetch request. Okay, what we want to prefetch next. So for every prefetch decision, Pythia again gets a reward from the environment, which it uses to learn the correlation between this program feature and what to do to make a successful prefetch prediction. Okay. So now let's try to go deep into defining these three key pillars of reinforcement learning, namely the state, the action, and the reward. So how do we define state? So as I said, like state is defined as a vector of program features. Features is what we are discussing till now. So let me define it more concretely. That feature has two components, at most two components, the control flow and the data flow information. So what are the control flow information? For example, the program counter address, right? The branch program counter, the branch PC. Maybe you can also think of, let's say, sequence of programs. So it's basically, this type of feature can give you a feedback of what is the path of the execution going in the program. And some examples of the data flow information can be, let's say, cache line address information, physical page number, delta between two cache line addresses, and literally any combination of these values also. So let me give you a concrete example of what the feature looks like. The state information looks like. So in this case, this is a state which is composed of two features. So the first feature is PC plus delta. The second feature is the sequence of last 4 delta. The first feature is further composed of control flow information PC and the data flow information cache line delta. The second feature is completely based on the data flow information. It doesn't have a control flow information, but it has some sort of history of data flow information, which is the last 4 deltas. Okay. So, okay. So now, do we have any question? Okay. So now let's define what is the action. So the action is defined as that given a demand access to address A, the Pythia's action is to decide which prefetch offset we want to prefetch. So it basically says that, okay, I have seen a demand to access address A, then I'm going to prefetch for A plus O next. That's the idea. Now, if in a processor that has a traditionally sized 4 KB page and 64 byte cache line, we have only 127 actions in the range of -63 to +63. Now, why do we want to limit why do we want to limit the action space in this range? Because it basically says that, okay, your prefetch cannot exceed the physical page boundary. Why do we want to limit to the physical page boundary? We can discuss offline. There are multiple reasons why we focus on prefetching within the same physical page itself. But also keep this in mind that zero offset, which is part of this range, right? So zero offset is also a valid prefetch decision for Pythia. So it essentially says that, okay, Pythia actively tries not to prefetch anything, and we'll see like that has implications when, let's say, you're based on the system level feedback. Pythia can actually decide whether okay, I'm not going to prefetch anything because it's going to overshoot your bandwidth consumption. So we are going to see the use case of this. But in reality, when we design the Pythia, we are not going to use the entire action space. We have truncated down the action space a lot. And we have mentioned in the paper itself, like how to do a systematic analysis of reducing the action space heavily, so that we can end up using the same performance without losing any accuracy itself. Okay, so now let's define the reward. So the reward is probably the most quintessential part of defining any RL-based system. So reward in this case defines the objective for Pythia, which encapsulates two key metrics: the prefetch usefulness. Basically, it says that, okay, how accurate your prefetch is, how whether the prefetch was late, whether it went out of page, and so on and so forth. And also it encapsulates system level feedback information. For example, memory bandwidth usage, cache pollution, energy consumption, everything. Now, I need to give a brief, let's say, example here that our framework can be extended equally well for incorporating any type of system level feedback. But for a concrete discussion, right, we're going to only focus on memory bandwidth usage as an example of a system level feedback throughout this paper, as well as throughout today's presentation, right? But that does not mean that the framework is only limited to incorporate memory bandwidth usage, but you can literally learn from any type of system level feedback possible. Okay. So this is how the rewards are defined. So rewards are defined in 7 distinct reward levels. So these are the reward levels, right? Each reward level essentially corresponds to a different usefulness of a prefetch request. For example, if the prefetch is accurate, as well as you have predicted it much timely ahead, then that's the reward accurate and timely. For example, if the prefetcher is inaccurate, so basically you have predicted something and the program has not demanded at all, so that's the inaccurate reward level. And if you see that inaccurate and the no prefetch reward levels are again further categorized based on the memory bandwidth usage. So we're going to see like what it means when it comes to the let's say the objective, defining the objective for Pythia in the next slide. And now, so the value of these reward levels are set at design time. So we do some systematic analysis of automatic design space exploration to set the value. If you are interested in how to set these values, please feel free to go through the paper itself. But that being said, these values are not actually statically fixed at design time also. So you can change the values in runtime via simple customization registers, which actually provides different performance objective to Pythia also. So what do I mean by this? So let me give you a concrete example. So let's say, what does these values mean, and how changing this value basically gives a different objective to Pythia. Okay. So this is what the baseline flat, so let's say vanilla Pythia configurations reward value that we have set. So as you can see, this is the accurate timely, accurate late, and so on and so forth, right? So if I set the Pythia's reward values like this, so we are providing actually 3 key, let's say, objectives to Pythia. So let's decode how these reward values are converting to an objective. So the first thing is that we are providing much more perks to Pythia if it generates an accurate prefetch request. So what does this mean? It means that whenever possible, if Pythia generates an accurate request, it's getting much more higher perks. So eventually it would actually get greedy to generate as much as accurate prefetch request as possible. Okay. But now if Pythia has a sense that, okay, the prefetch might not be accurate based on the correlation that we are seeing, then what happens? Then in that case, if the bandwidth consumption is relatively low, right, then we are providing a slightly higher, higher in a sense, like -4 is higher than -8, but it's still worse, right? So worse than plus 12 and plus 20. So it's basically saying that if your bandwidth consumption is low, you still slightly prefer predicting nothing rather than predicting something inaccurate. So in this case, so it basically says that if your bandwidth consumption is low, Pythia would essentially try to, stay on the conservative side slightly rather than, aggressively predicting something bullshit. But then if your bandwidth consumption is high and Pythia is also feeling that, okay, there is a possibility that this prefetch is not going to be accurate, then Pythia clearly has a much more perk to stay predicting nothing rather than predicting something inaccurate. So in this case, what happens is that if your bandwidth consumption is high, then Pythia would strongly prefer not to predict something rather than predicting something inaccurate. Okay. Now, if I change this reward level values just by a slight bit, so it's basically what we did is it used to be like this. Now, what we are going to do is we are going to increase the reward levels for no prefetching, both in case of low bandwidth and the high bandwidth. And we are decreasing severely the rewards for inaccurate prefetching. So basically it goes to this side and the reward for inaccurate goes to that side. So then what happens if I set it like this? So in this case also, we are still providing, much more perks for accurate prefetching. So, Pythia would still continue to generate accurate prefetches whenever it's possible, because that's the highest performance benefit that we are providing. But if Pythia cannot generate accurate prefetching, then what happens is that it clearly has a much more benefit, much more perks to, prefetch nothing rather than prefetch something inaccurate, irrespective of the bandwidth consumption. So what happens in this case is that it would simply stay put and do not prefetch anything at all. So it basically goes into a much more conservative domain. So this type of configuration is what we call a strict Pythia configuration. And it's especially useful when you're designing a server class processors where you have like extremely highly threaded processor, but then you have limited main memory bandwidth. So your memory bandwidth per core is extremely limited. And also if you're executing, or let's say if you're running memory bandwidth constrained workloads, for example, let's say large scale graph analytics workloads, where your performance is actually directly correlated with the bandwidth sensitivity, the bandwidth consumption of your main memory. Then in those cases, this type of configurations actually makes much more sense. Okay, so do we have any questions till this point? Because this is essentially what the crux of Pythia is, like how we can change its objective on the fly, and how it basically molds into the prefetch decisions it makes. Okay, if we don't have any questions, let's move forward. So let me give you a brief overview before jumping into the evaluation, how Pythia looks like in reality actually. So Pythia is composed of two key components: the key value store, which records the Q value pairs of all state action pairs. So this is nothing but just a flat collection of tables. That's what it shows. This is exactly how it's implemented. And then the other key component is the evaluation queue, which is a first in first out queue of recently taken prefetch decisions. So basically this evaluation queue stores which state has decided to Pythia has decided to take this action in this state, as well as which address that you have predicted for taking this action. Okay. So for every demand request that the program generates, Pythia first checks the evaluation queue with the demanded address, basically to see, okay, my program is trying to access this request. Have I generated this have I generated prefetch for this request before or not? So that if you have generated this prefetch request, it's likely to be present in the evaluation queue. In that case, Pythia would simply assign a reward to that evaluation queue entry, saying that, okay, I have generated this prefetch request for this guy, and this memory address is also now getting demanded from the core. So that means my prefetch request is correct actually. Okay. So now once we do this, then the second stage is we extract a state of program feature from the demand request. That's the state vector that we have seen. And then we use that state vector to look up the Q we store to extract the Q values from that table itself. Now, based on the action that has the maximum Q value for that state vector, Pythia would use that action to generate the prefetch request and inject the prefetch request to the memory hierarchy. Okay. At the same time, Pythia also uses the same memory, the same prefetch action along with the state action pair, and also records this in the evaluation queue, because that would be useful in the next time when some demand request comes. We need to check it and verify that, okay, have I generated prefetch request for that guy or not? Okay. And so every insertion to this evaluation queue, as I mentioned, this is a FIFO queue. Every insertion to the evaluation queue also evicts something from the front of the queue. So whenever you are evicting something from the front of the queue, you use that evaluation queue entry, the state action pair that is stored inside that entry, as well as the reward that you have already assigned to the evaluation queue entry to update the queue value store. So that basically closes down this feedback loop, and this feedback loop itself basically keeps on training the predictor on the fly. And just the last piece of the puzzle is that whenever your prefetch request is actually coming from the main memory and getting filled into the cache hierarchy, we would also set the field bit to the evaluation queue. So this is required to understand whether the prefetch actually the prefetch was filled first, or the demand for this that request came first. So yeah, I mean, if you go to the paper, we have mentioned like why prefetch fill hints are, how prefetch fill hints are actually used for understanding the timeliness of the prefetch request. Okay. So yeah. So that being said, there are many more many more information in the paper itself. For example, the pipeline organizations, like essentially how we have designed this entire queue value store to make it as small as possible, at the same time do a fast lookup whenever we want to make a prediction. There are many other let's say intricate details about the mechanism, like for example reward assignments, how the automatic designs for exploration works, let's say which features that we want to set it from the get-go, which actions that we like the action space pruning that I just mentioned, the reward and the hyperparameter values, and many more information in the paper. And I'll encourage everyone to go through the paper, and if you have any interest in this direction, just feel free to ping us. And yeah.
One question. So
sure.
Step you only prefetch one location, right?
Yes.
So is it possible to, let's say, I prefetch A plus 2, A plus 4, A plus 6, one decision?
That's a very good question. So in our evaluation, we actually learn let's say these actions, right, that I mentioned before, like the A plus O, right? So we'll only learn that O from this feedback loop, which offset that you want to predict. And then we have a degree that you're mentioning. Let's say once you have decided that, okay, Pythia wants to take this action A2, then I would actually prefetch A2 ahead, and then 2A2 ahead, 3A2 ahead also. So it's basically given let's say given your address is let's say X, you would prefetch X plus A2, X plus 2A2, X plus 3A2. So that's the degree that you're mentioning, that okay, it can also go deeper into the execution prediction. Does that answer your question? Okay. Yeah, that's a good question actually. So, but given that said, I think there is still opportunity left in this work to the thing that you alluded to, right? That this is one way of going deeper into the look ahead, that okay, A2 and then 2A2 and then 3A2. But what if let's say A2 is the maximum confidence, let's say A2 that gives you the maximum Q value, but let's say A1 is the second maximum. Maybe A1 is also equally good for a prefetch candidate, right? So can I also prefetch, A2, A1, both of them? Or maybe can I also prefetch, let's say, top 3 candidates, let's say top 4 candidates? What happens in those cases, right? I think there are opportunity left to explore on that direction also. If you're interested, then yeah, definitely we can talk. Okay, so now let's go to the evaluation. So yeah, for this we will evaluate the Pythia using ChamSim trace-driven simulator. We are going to use this same simulation infrastructure, well, pretty much similar infrastructure in the lab that you're going to see next, the prefetching lab. We are going to use 150 single core main memory workload traces, as well as multiple multi-core workload traces for evaluation, and we're going to evaluate against multiple prior state-of-the-art prefetches, just to properly understand, like, let's say, how it's better and quantify its betterment, right? So okay, so now let's first analyze performance improvement across a wide range of core configurations. So on the x-axis, you are seeing the number of cores. y-axis, you are seeing the performance improvement on top of no prefetching baseline. Okay, so this is how the prior prefetchers perform: SPP, MLOP, and Bingo. I'm just taking 3 as a sample in this case, and this is how Pythia performs. So what it shows is that in single core, you have a performance improvement of 3.4%, and in 12 core, you have a performance improvement of 7.7% on average. So what this says, there are 2 takeaways from this figure. First, for every core configuration, you are seeing that the red bar, the red line is actually above all the other lines. So it basically says that it consistently provides high performance across all type of core configurations. Okay. The second observation is that if you see the performance increase from performance benefit is increasing from the single core to the extremely high core configurations. So what the second key takeaway is that, okay, your performance improvement also increases with the increase in the core count. Okay, so now let's try to evaluate Pythia in a different metric, which is scaling the DRAM bandwidth consumption. So in this case, we are only seeing single core simulation, but then we are scaling the DRAM bandwidth all the way from 12,000 million. Sorry, I mean it's like 12,000 million transfer per second to 100 million transfers per second. So it's essentially, the more you're going to the negative direction of the x-axis, your bandwidth is basically getting limited and limited. Y-axis, you are seeing the performance improvement, and 1 is basically the line that basically says that even if you don't do prefetching, that's basic. You should have been there. It should not be lower than the no prefetching baseline. Right? So this is how the prior prefetchers perform. As you can see, the more you go to the bandwidth constrained configurations, performance actually tanks. And in some cases, in extremely bandwidth constant configurations, performance tanks even lower than the baseline. Baseline means it basically says that if you don't do prefetching, don't do anything, it still would have been better than having the prefetcher itself. And these configurations are not actually, they are realistic configurations. You can see the base. So this is our baseline. And all these configurations are actually realistic configurations that are coming from, real life processors. For example, AMD Threadripper, EPYC Roman, and Intel Xeon processors. These are the per core main memory bandwidth of the available to these processors itself. So if we evaluate Pythia here, so Pythia works like this. So as you can see, like for every main memory bandwidth configuration, all the way from the extreme high bandwidth configuration, where it's providing 3% performance benefit on top of MLOP, and all the way up to the extremely bandwidth constant configuration, where the same guy who was actually best in our baseline configuration is not best anymore, right? But still, from that guy, it's 17% performance improvement. But even the next the best configuration for the bandwidth constant scenario, it still maintains a decent performance competitive edge basically. So the key takeaway from this figure is that Pythia outperforms multiple prior prefetchers across a wide range of bandwidth constant configurations also. Okay, so yeah, I mean, all this performance benefit comes at a modest cost of 25.5 KB of storage overhead. We have also evaluated Pythia and its entire complexity. I mean, to be honest, it's not entirely simplistic, but it's just to see what is the complexity looks like in the actual hardware. We have evaluated Pythia using Chisel hardware descriptive language also, and we see that Pythia only incurs a minor single point area overhead. Only half a point power overhead on top of a desktop class 4-core Skylake processor, while also simultaneously satisfying prediction latency requirements required for this prefetching. So, as I said, this entire infrastructure is open source. You can simply download and play around with it. You would get all the traces that we have used for this evaluation. Some of these traces you are going to use for the prefetching lab also. You would get the ChamSim source code, you would get the Cheese and modeling code, everything there in the repository. So yeah, if you want to, if you're interested in extending this idea also, just let us know. We'll be happy to discuss more along these lines. So yeah, so that brings me to the conclusion. So I would go to the conclusion if I don't have any question from you guys. Do I have any questions? Probably not. Okay. So yeah, then let's conclude the talk. So as I say, in this work, we are basically targeting on 3 key shortcomings from prior prefetches. They mainly use only single program feature. They lack inherent system awareness inbuilt into the algorithm itself. They lack in silicon customizability. And to alleviate these challenges, the goal of our work is to design a prefetching framework that learns from multiple program features and inherent system level feedback on the fly. And it can be customized in silicon to use different features as well as different prefetching objectives. And towards this, we propose Pythia, which formulates the prefetching as a reinforcement learning problem. And we show by extensive evaluation that Pythia outperforms multiple state-of-the-art prefetchers across a wide range of main memory bandwidth, wide range of core configuration, let me put it like this. And yeah, as I mentioned before, it's completely open source, just play around with it. So that concludes the first presentation. The last round of questions, if you have anything. Yeah, go ahead.
When you have a context switch, does the predictor go?
That's a good question. Okay, so in our evaluation, we have not actually modeled context switching, right? In a sense that, let's say in a realistic context switching, in a sense that, okay, what happens in the actual processor, right? But we have, to answer your question, it actually starts from scratch. If you switch the context, and when the same context comes back, you are not saving the context when it switched out. So you have to start from scratch. Now to address the problem that you might be alluding to, that okay, then how much time does it take to learn from the scratch then, right? So we have actually evaluated using a different warm-up length. So warm-up in a sense that you would see this in the prefetching lab also, that when we are, or maybe you have already seen it in some other labs. So when we do architectural simulation, right? So we have some sort of warm-up phase and then the simulation phase. So warm-up phase essentially warms up the components present in the processor, let's say caches or let's say prefetches for that matter. And then once your warm-up is done, you do the simulation part. So why do we do the warm-up? Because we want to characterize the behavior of a processor when the processor is actually running, right? The steady state behavior, basically. So we don't want to characterize the processor when it boots up, right? So that's why we have this warm-up phase and the simulation phase. But in this evaluation, we have actually done this thing that, okay, what if your warm-up actually becomes very less, right? So it basically says that, okay, how quickly you can actually start learning. And we have seen that we have made the warm-up to be 0. I mean, not exactly 0, let's say, only a few hundred instructions. So that's nothing as compared to, let's say, the traditional warm-up of 100 million instructions warm-up, right? And we have evaluated 500 million instructions after that without having any warm-up. And we still see that Pythia outperforms, prior prefetches. It basically says that even if you start from scratch, right, it still learns as fast as, it still learns fast enough to provide performance benefit and have the competitive performance edge on top of the previous works, basically. Does it answer the question? Yeah. Okay, one question. Yeah, go ahead. Yes. Mm-hmm. Schedulers in the sense the main memory scheduler. For sure, yeah, for sure. I think so, yeah. So like main memory scheduler has a very strong, let's say, use case for this type of high core configurations, right? I mean, we have discussed the reinforcement learning based memory controller design in the previous past lectures also, right? So it basically says that when you have, let's say, multiple cores are exercising and going through the same memory controllers, right? The main memory controller, how it's actually prioritizing request over the other, that also has much, let's say, performance impact that we can extract out of the system. Now, the proposal that we are saying that, okay, should the prefetcher also interacts with the main memory scheduler to, holistically learn across this thing? I totally agree that it should be. I mean, this is one way, or let's say one baby step to, incorporate one set of, let's say, system level awareness, right? Let's say main memory bandwidth. But we are not literally, let's say, dictating the main memory controller also that, okay, I am seeing that this is the main memory bandwidth, so that you need to co-optimize the prefetcher as well as the main memory scheduler, so that you extract even more performance benefit from the same configuration. And I totally agree that this is like a good research direction to co-optimize also. Yeah. Any other questions? Yeah, go ahead. Okay. So ideally, it should be measured as that you have prefetched the data to the cache, right? And you're evicting that data from the cache. At that point, you want to see whether this data was prefetched to the cache and you have not used it, right? Then you know that, okay, your prefetch is basically useless. So that's the ideal scenario. But in this case, what we are doing is that this evaluation queue is somewhat mimicking that part. Mimicking in the sense that whenever you generate a prefetch request, you add it to the main memory hierarchy, as well as you also add it to the evaluation queue. So the evaluation queue essentially, in our evaluation, it's 256 entry long. So it basically says that it's actually keeping track of last 256 prefetches that you have done. And within that, so whenever you have inserted one entry to the evaluation queue, that evaluation queue entry basically flows through the tail of this queue to the head of the queue. So it basically gets some time to see a demand reuse from the core. Within that time, if that evaluation queue entry does not see any reuse, then I would consider that, okay, this prefetch request is not going to be reused in the future also. So that gives us this feedback that, okay, I'm kicking someone out from this evaluation queue, but that guy has not been demanded yet. So that means, it's basically not going to be used by the program. I mean, I agree with this fact that this is just a mimicking, right? But we can also make it, let's say, better if we, piggyback this information to the cache hierarchy itself, saying that, okay, I have fetched this data using this information, right? And whenever this cache line is getting evicted from the cache, then you are going to check whether you have already used it or you are not, you haven't used it. And so does it answer the question? Okay. Any other question? I mean, these are good questions. I think the context switching, the degree, these are definitely something that we have actually plans to look into these problems also. So yeah, and these are good questions actually. And also the memory controller interaction. It's yeah.
Next paper.
Okay. So we have
1 hour.
really okay.
I don't.
Yeah, that's true. Okay, let me post through the next paper then pretty quickly. Okay, so again, the next paper is called Hermes Accelerating Long Latency Memory Request via Perceptron-Based Off-Chip Load Prediction. So the key idea again is coming from the same fact, and then, as I said, like these works are synergistic to each other, right? So we have seen Pythia targeting the prefetching part of the hierarchy of the conventional latency tolerance technique. And in this work, we are essentially going to, synergistically see what is happening for the out of order execution, caching, as well as prefetching for this work. Okay. So the name of this work is Hermes Accelerating Long Latency Load Request via Perceptron-Based Off-Chip Load Prediction. So the key problem that we are seeing in today's processor, right, that the load requests that are going to off-chip, they're still problematic, right? Problematic in terms of performance. Why? Because they often stall processes by blocking instruction retirement from the reorder buffer. So reorder buffer is something that architects have used for implementing the out of order execution. So that's the window of instructions that you can execute out of order so that you can extract instruction level parallelism. So we have seen that even we have grown the reorder buffer by quite a lot. Still, off-chip load requests are actually blocking this instruction retirement from this reorder buffer. And as a result, they have severe performance penalty. And as I said, like architects have designed like those four techniques, and we are going to focus on these two techniques in this work: sophisticated prefetchers, as well as increasing the size of the on-chip caches. Now, what we are seeing here is that, sophisticated prefetchers like Pythia that we just mentioned, right? They are actually good. They're actually good in terms of prefetching a significant fraction of the off-chip load request. So this is the entire pie is the off-chip load request that you can see without having any prefetcher. And as you can see, like 50% of them are actually successfully predicted by a state-of-the-art prefetcher like Pythia. But then the remaining 50% are still going to off-chip, even if you have a state-of-the-art prefetcher like Pythia. And out of those 50%, if you focus on narrow down to that request, 70% of them are still actually blocking the instruction retirement from ROB. So basically, we have a decent amount of performance improvement on the table if we can, reduce the latency of such requests. And when it comes to latency requirements, if we focus on that 50% requests that are still going to off-chip, even if we have a prefetcher, we are seeing that on-chip cache access latency significantly contributes to the total off-chip load latency. So this is what the timeline looks like if you go to off-chip, right? That's the main memory access. So what we are seeing that if you just simply remove the on-chip cache access latency from the critical path, 40% of the stall cycle caused by this load requests are completely gone. So that's the goal of this paper, is to reduce this latency. Now, as we are seeing, let's say, the caches are actually getting bigger and bigger through the generations. They're also getting slower. So this is a work from 2007, which actually shows that the on-chip cache size are increasing by significantly, and as well as the heat latencies are also increasing. We have seen the similar type of trends, and these are the 5 recent generation of Intel processors. As you can see, like the L2 cache, I'm plotting just the L2 cache in this case. L2 cache size is also increasing, as well as the L2 cache latency. So what it basically says that as we go into the future and we exercise more and more cache sizes on the processor, the caches are bound to get slower. So to alleviate the challenges that are stemming from the long latency on-chip cache access, the goal of this work is to improve processor performance by removing the on-chip cache access latency from the critical path of the off-chip loads. So towards this, we propose Hermes. The key idea behind Hermes is twofold. So first, Hermes predicts which load requests are likely to go off chip. And second, it starts fetching the data directly from the main memory, while it also concurrently accessing the cache hierarchy. So I'll go to the detailed analysis of what Hermes looks like in the reality, but let's see the key contribution. So to enable this, the off-chip load prediction, Hermes employs the first Perceptron-based off-chip load predictor that predicts which load requests are likely to go off-chip by learning from multiple program context information only. Okay, so now let's try to understand how Hermes works. So this is how the traditional cache hierarchy looks like in today's processor, right? So you have the core, and then you have a increasingly large cache hierarchy, and then you have the main memory, which is accessed behind the memory controller. So in a traditional baseline, this is how the main memory access timeline looks like, right? So if your processor's latency tolerance limit reaches here, so basically it can tolerate latency up to this point. Then for the remaining part of the latency, the processor simply stalls. Okay. Now Hermes essentially employs a Perceptron-based off-chip load predictor, which we call Puppet. So for every load request that are getting generated in the core, Hermes consults Puppet to predict whether this load is likely to go off-chip or not. If the load is predicted to go off-chip, then Hermes waits for the address translation to finish, because the address translation, the core generates a memory request using a virtual address, but then you need to have a physical address to access the main memory. So Hermes waits for the address translation to finish, which happens in parallel with the L1 Dcache lookup. And then once the physical address is available, it issues a direct request directly to the main memory controller to start fetching the data from the main memory, while also concurrently accessing the cache hierarchy. Now, if the prediction is correct, the request that is flowing through the cache hierarchy, it would eventually miss the LLC, and it would arrive at the memory controller, where it will simply wait for the ongoing data transfer to complete from the main memory. Once the data comes back from the main memory, Hermes simply returns the data back to the core, thus saving significant amount of stall cycles, which essentially provides a performance benefit. Once the data goes back to the core, Hermes trains the off-chip predictor so that it can keep on learning how to accurately decide which predictors, which load requests are likely to go off-chip. Okay. So now let's discuss how to design this off-chip load predictor. So as it says that there are multiple prior works in the literature that uses that can be used to design off-chip load prediction in some way. So history-based off-chip prediction, as we can see, it's employed in 1999, right? So they have been employed in understanding load requests that are going to miss in the L1D cache using branch predictor-like structures or hybrid structures. There is the other types of prediction technique is by explicitly tracking cache content. So the key idea here is that if you know which data blocks are present in the cache and data blocks are getting evicted from the cache, you know which load requests are going to be serviced from the cache hierarchy also. But then this has two key caveats. First, it requires a large metadata structure and the size of the metadata also increases with the cache hierarchy size. And second, it may need to track all operations that are going into the cache hierarchy, which might actually get very tricky based on the the cache hierarchy configuration. So the Hermes and Puppet, for that matter, in our design, takes a completely different approach. It says that the key idea behind the learning-based approach that we are employing here is that the program itself can dictate for what's going to happen with the microarchitecture itself. So the idea here is that you correlate different program features to predict whether this load request is likely to go off chip or not. And by that way, we show that we can enable high accuracy off chip prediction by employing low storage overhead as well as low design complexity. So in the paper, we have used predictors that are inspired from these prior works, and we have shown that Puppet significantly provides higher accuracy as well as higher performance than predictors that are inspired from these works. And if you're interested, definitely go through the paper also. So now let's try to understand how to design this sort of, let's say, perceptron-based off-chip predictor design. So we are going to use multi-feature hash perceptron model for designing this off-chip load predictor, which has been extensively used for branch prediction literature, and we are going to use it for different types of prediction for, in this case, the off-chip prediction. So each feature has its own weight table where the weight shows a correlation between the feature value and the off-chip prediction. Now, when we want to make a prediction, the prediction we just want to use simple operations like table lookups, addition and comparison operations. So let me give you an example of how the prediction works. So in the first stage, you extract a set of program features from the load request. And again, the program feature is exactly the same idea of what I was mentioning in the previous lecture also. It's like, some sort of control flow information as well as data flow information merged together. It might have both of them. It might have just only one of them also. Like, for example, PC plus offset is a program feature. You can think of many other program features for that matter. So that's the first stage. You extract a set of program features. Second stage, you hash down the program feature value and use that hash value to retrieve the weights from these individual weight tables. In the third stage, you accumulate all the weights and use the cumulative weight to compute an activation function. The activation function essentially says that it's just simple, greater than equal to function. If the cumulative weights is higher than the activation threshold, which is statically fixed at design time, you would simply say that, okay, this load is likely to go off chip. Now, you might be questioning that, okay, how to train this thing? I mean, how this thing can even work, right? So to train this, let's take this example only. Let's say, for example, let's say this load, let's say for predicted to go off chip, but let's say in reality, that load didn't go off chip. So what happens in that case? So it basically says that the activation which have actually happened for that load shouldn't have happened. It basically says that your cumulative weights is what you got is higher than the activation threshold. So you need to lower it down. So in that case, Puppet again indexes all the weight tables using the feature value again, and simply decrements each individual weights. So that's, by using simple increment and decrement operations, you can continuously learn from this set of program feature itself And these learnings are actually stable enough to predict accurately which load requests are likely to go into the future, way ahead in the pipeline. So now let's try to evaluate this entire idea, like how this evaluates. So for this evaluation, again, we are going to use the ChampSim trace-driven simulator across a wide range of memory-intensive traces spanning across these workloads. And not only we are going to evaluate Hermes on top of, let's say, multiple prior prefetches, and then obviously you can see Pythia is incorporated in this list. We are also going to evaluate Hermes against two types of off-chip predictors that are inspired from prior works, as well as an ideal off-chip predictor which simply knows which load requests are likely to go, load requests are going off-chip. That's basically the ideal version of this predictor. Okay, so now let's, for our evaluation, we are going to use a 5-cycle L1D, 15-cycle L2, and 55-cycle LLC round-trip latency. Now, for the latency for Hermes to issue a request directly from the off-chip predictor to the main memory controller, it actually depends a lot based on how we are designing the interconnect between these two components. So for that matter, for that reason, we have actually simulated the configuration, and we have swept this configuration from all the way up to 0 cycle, which essentially mimics a very aggressive idealistic interconnect design, and then all the way up to 24 cycles, which is a pessimistic estimate of interconnect design. But for the brevity of this lecture, we are going to see the performance numbers coming from the 6 cycles. But these 6 cycles is nothing, it's not nothing important. In the paper, we have also mentioned like 6 cycles and 18 cycles. It's just for sampling. Okay, so let's first analyze the performance improvement. So on the x-axis, you are seeing the workload categories. Y-axis, you are seeing the performance improvement on top of no prefetching system. Okay, so this is how the performance improvement looks like. The orange bar is the Hermes, blue bar is the Pythia, which is the prefetcher that we had just seen in the previous lecture. So what we are seeing here is that Hermes alone, like just implementing by itself, nearly provides half of the performance improvement that Pythia full-blown prefetcher can provide, while only consuming 1/5 of its storage overhead. I'm going to come to the storage overhead later, but yeah, Hermes is much more lightweight and still provides almost nearly 50% of the performance improvement. The second observation is if we combine both of them on top of each other, that additionally buys a 5.4% performance improvement on average across all workloads. And the third observation is that if we evaluate Pythia on top of an ideal Hermes, that basically knows exactly which load requests are going to off-chip. Basically, that's the ideal predictor with 100% accuracy and 100% coverage. We are seeing that our version of Hermes actually comes nearly 90% performance benefit of that idealized Hermes version also. So that basically says that the prediction is going into the correct direction. Now, performance is only giving the partial part of the picture. We need to also see how much memory bandwidth consumption, or let's say the increase in the main memory requests are coming from these configurations. So this is that figure. On the x-axis, again, you have the workloads. Y-axis, you have the increase in the main memory request on top of a no prefetching system. So what we are seeing here is that on average, if you implement Hermes, that increases the main memory request by 5.5%. If you implement Pythia, that increases main memory request by 38.5%. So it basically says, and if you implement both of them together, then it additionally increases main memory request by 6% on top of it. So what it basically says, it says that if you compare these performance numbers, right? If you compare these numbers with the performance number that I just mentioned in this previous slide, right? So what it basically says that those are the performance numbers. So what it says that if for every 1% performance benefit that these techniques are providing, Pythia actually increases the main memory request by as much as 2%. Hermes, if you implement on top of Pythia, that increases by 1%. And if you implement Hermes alone, that increases by only 0.5%. So this essentially shows that Hermes is much more bandwidth efficient, even a bandwidth efficient prefetcher like Pythia that we have seen previously. Now, if you go into let's say for this reason, if you evaluate Pythia across wide range of bandwidth configurations, also what we are seeing is that again these configurations are coming from realistic configurations, and as you can see, Pythia actually tanks performance because we have also incorporated different types of prefetcher, different types of traces in this work, in this version of the work, which were not actually available and in the previous version. Is basically like many more server workloads, which are much more memory bandwidth demanding. So what we can see here is that if in extremely bandwidth constant configurations, Pythia Hermes actually starts improving, starts outperforming Pythia also. And if you combine both of them together, then the combination curve lies definitely ahead of the Pythia curve itself. So that basically says that Hermes definitely contributes as a adjunct technique that we can implement on top of any on top of the prefetching techniques that we know that we have seen in these lectures. Now, all this evaluation that I'm just mentioning, I mean, you might have seen that, okay, Pythia is the underlying prefetcher that we are mentioning, but there is nothing special about Pythia and Hermes. In fact, we have evaluated Hermes on top of multiple prior prefetchers, and we are consistently seeing that, okay, if we implement Hermes on top of other prefetchers also, that also improves performance benefits. So that makes us believe that, okay, Hermes can be incorporated on top of any baseline prefetcher also. And all this performance improvement, as I mentioned, comes at a modest cost of 4 KB storage overhead and a single person power overhead on top of a Alder Lake-like performance core configuration. I'm not going to cover all the other results. There are many more results into the extended version of the paper, especially in the archive. And feel free to go through the archive version. And definitely, if you're interested in exploring these directions, definitely feel free to reach back to us. So just to summarize everything that I'm just mentioning, so Hermes essentially advocates for off-chip load prediction, which is a fundamentally different form of speculation than load address prediction employed by prefetchers. And we see that off-chip load prediction can either be applied by itself, or it can be combined with load address prediction to provide additional performance improvement. And in a nutshell, Hermes employs the first off-chip perceptron-based off-chip load predictor that provides high accuracy and high coverage off-chip prediction while incurring very modest storage overhead, as well as it provides performance improvement on top of an extremely strong baseline that has state-of-the-art prefetchers implemented. And most importantly, it provides better performance for bandwidth trade-off. So that being said, I truly believe that the off-chip prediction employed in Hermes can be made even better. And again, for that reason, we have open sourced this entire infrastructure. In this infrastructure, you will get all the workload traces that we have evaluated, every type of prefetchers that we have implemented throughout our research work, as well as 9 types of off-chip predictor implementation from the scratch. So if you want to play around with this system, just go nuts. That being said, you can pretty easily extend this framework, implement on your own off-chip predictor. And I truly believe that off-chip predictor should be or it would be made even better. So you can pretty easily extend the base class, implement your own train and predict function. It's just pretty it's just good to go. You would get statistics like precision and cover, like recall, basically the accuracy and the coverage pretty much out of the box, something similar to this one, which you can use fine tune to the implementation as far as possible. So with that being said, I hope that off-chip prediction can enable further optimization, not only the one that we are seeing here, but many other optimization. For example, prioritizing loads that are likely to go off-chip in cache queues, as well as on-chip network routing, better instruction scheduling for data-dependent instructions, and maybe many more ideas that not only targets performance improvement but also fairness in today's extremely highly threaded processor design. And with that hope, I would conclude Hermes here. If you have any questions, let's take it now.
We have time. We can get back on time.
Yeah. I mean, I think we have few minutes if we have any questions. So these two are the kind of an example of how lightweight machine learning driven approaches can work for optimizing a traditional problem, right? It's a hard problem for memory latency optimization. Yeah. If you have any.
Maybe I have a question.
Sure.
Yeah, this is, I think both of a question that's a bit challenging
Okay.
for you, let's say. So Hermes is kind of odd in the sense that people are building these huge cache hierarchies, and you're trying to bypass the cache hierarchy.
Mm-hmm.
Why not go a next step further and just do the computation on the memory side? Basically, why deal with bypassing the cache hierarchy? You know that the data is in the memory side, just do the computation over there.
I think okay, so that's the question, right? So we have actually, and this is a very good, valid question, and we have discussed this with our collaborators, and Mohammed is sitting over there, right? So we have discussed, and Juan is also sitting over there. So we have discussed this like extensively, that this type of, let's say, hint, right, that your data is not actually present in the cache hierarchy. It basically can also give you a hint that, okay, you need to, why don't you, instead of bringing back the data, why don't you offload the computation there itself? So what I'm what we are alluding to is that this sort of hint can also be used. I mean, maybe we have to design it better, but this sort of hint can also be used to understand when to offload a computation to the main memory, rather than fetching the data from the main memory to the processor. So they can actually be used for, let's say, if you know that, okay, this particular load is going to miss in the entire cache hierarchy, so why don't we offload that load and any further instruction that are dependent on that load, a small, let's say, dependency chain, to the main memory itself, which basically says that, okay, instead of fetching the data back to the core, pull the computation to the memory, right? So we can actually think of this as a hint, and hopefully some other hint also, which I think which we need is also another hint to say that, okay, if I fetch the data to the cache hierarchy, will it be reused from the cache hierarchy? If we can have those two hints, so basically the first hint says the data is not present in the hierarchy. The second hint says that even if I fetch the data to the cache hierarchy, it's not probably going to be used. And both these two hints together can actually make a case for offloading the computation to the main memory rather than fetching the data altogether.
That makes a lot of sense, I think.
So,
it's
yeah, I mean,
good to explore for future work, for sure.
Yeah, so we have discussed this with some of our folks. So yeah,
It also has synergies with what was briefly mentioned in Juan's lectures, PIM-enabled instructions, right? If you have PIM-enabled instructions, that's essentially what you're trying to do.
exactly.
You're offloading instructions, but I think it makes more sense to offload the dependent instructions as well.
Exactly.
And since you're doing the offloading from the processor, you get rid of a lot of the virtual memory and coherence issues, just like PIM-enabled instructions discusses.
Yeah. It's not just one instruction, it's also the dependence chain, right? So yeah. Yeah. So if any one of you also wants to, brainstorm, this is actually, I think, one can also agree with this, right? So this might be a good direction to explore also. Okay. Makes sense.
And I also think that some interesting study how compare prefetching to putting in media. Also think about how much probably you will need, but maybe
Co-optimizing prefetching as well as offloading the instruction itself. Yeah. Yeah, I agree with this. Okay, if we don't have any question, I think let's give it to the next presenter.
I think we should take a break.
Thanks everyone for listening.
Break. And then we can come back at 2:50. How long the other talks will take. And come with questions.
Thanks, everyone.
This is really annoying. How about now? Is this better? Okay. Okay, so Gagan is going to talk about, I still don't see it. Okay, I see it now, that green thing. Yeah, Gagan is going to talk about another application of reinforcement learning in hybrid solid state drives for data placement. And this was published in ISCA 2021. And 22, yeah, well, it should have been published in ISCA 2021, but it got published in 2022 because of multiple rejections, probably. Yeah. Okay, is that correct? Yeah. Kind of, approximately at least. Okay, and the source code of this is also available, right, online. Yeah, so you can experiment with these things, both Pythia. Actually, Pythia you can experiment with in your lab, in Prefetching lab. Hermes, maybe next year, if you take this course, you can experiment with things like that. And maybe Sibyl next year also, but feel free to. So because the source code of these works are all available, you can develop new ideas building on them as well. Okay, I'll leave it to Gaga. You want to use this one?
Yeah. Thank you, Onur.
I don't know which one do you want to share.
Just this one.
That's up too. You're sure? Okay.
Okay, it's working? Okay, awesome. Hello, everyone. Thank you, Onur. I'm Gagan. I'm a postdoc in the Safari Research Group. So as Onur mentioned, I'll present Sibyl, which is an adaptive and extensible data placement in hybrid storage system using reinforcement learning. Rahul already set the stage for reinforcement learning, so it would be interesting for you guys to see another application of it. It's a bit different flavor of reinforcement learning, so we are not using exactly the same thing. So you will get to see how we can use reinforcement learning in a different application. So first, I'll start with an executive summary. So hybrid storage systems consist of multiple different storage devices, which are used to provide high and scalable capacity at high performance as well. And there are multiple data placement techniques which are there in literature. However, we observe there are two key problems with the prior data placement techniques. First is the lack of adaptivity, which is to both workloads and also to device configurations, and also the lack of extensibility to more devices. So our goal in this work was to design a new data placement policy which provides both adaptivity, which can continuously learn if you change the workload or if you change the configuration. And also it provides extensibility to many more different hardware configurations, storage configurations, which are presently there or in future as well. So our contribution in this work is Sibyl, which is the first reinforcement learning based data placement technique, which provides both adaptivity and easy extensibility. And top of that, it's easy to implement and design as well. And we extensively evaluate Sibyl using real systems with a wide range of workloads. And we show that Sibyl improved performance by 21.6% on data placement techniques for dual hybrid storage configuration, and 48.2% for tri-hybrid configuration. And Sibyl is able to achieve 80% of the performance of an Oracle policy with a minimal overhead. So this is the outline of the talk. So first I'll go into the key shortcomings. Before that, I'll give a brief background on how hybrid storage systems look like. So over here, you can see a fast device and a slow device. So this is like a typical dual hybrid storage system. And then you have an application which is assigned logical addresses. So there are like multiple pages. And then we will have the storage management layer, which is in an OS. And this management layer is responsible for managing data around different devices. So all the read requests and the write requests have to be served from different devices. And also this storage management layer is responsible for promotion and also eviction. So for example, if your fast device is full, and you don't have enough space, then your data has to be moved from the fast device to the slower device. Or on the other side, like if you have some application which has a lot of hot pages, so pages which are being reused frequently, you would like to serve those kind of pages from the faster device and not from a slower device, because if it's in the faster device, then the request latency will be really low. And that's what the storage management layer is responsible for. So it's really critical in a hybrid storage system, these management layers and these data placement policies. And if you see, if there's an smart data placement policy, it should be able to exploit the characteristics of fast device. For example, this device has really fast latency, but the capacity is small. So it has to take into account those things as well. So in the end, the performance of a hybrid storage system highly depends on the ability of your storage management layer. And we observed in the past, there were many data placement policy which have been developed, but still there are a lot of shortcomings in these data placement policies. And we observe two key shortcomings. First is the lack of adaptivity to both workload characteristics and also changes in the device types and configuration. And then the lack of extensibility. So if you have like more devices, then these policies are not really easily extensible. So let's look into the lack of adaptivity. So if you have a change in workloads, so usually these policies, what they do, they look into a typical, like a static characteristic, for example, the size of the request, and based on the size of the request, they will serve the request from either from a fast device or a slow device. And these parameters, these characteristics, they are statically tuned during the design time. And these designers expect that these parameters are going to work for all the different scenarios, all the different workloads, which is not really true. So for example, over here, we have a CDE policy. On the x-axis, we have 4 different workloads, and on the y-axis is the request latency. So the lower, the better. And we implemented another policy, which is we modified, this one was for hybrid main memory. And so we modified for hybrid storage systems. And this is a supervised learning based techniques. And we wanted to make a comparison of these approaches to an Oracle. So this Oracle policy is impractical policy. So because it already has knowledge of future access patterns, so you can't really build this one. But in the end, what you would like to do is like get performance as close to Oracle policy as possible. And if we observe like these baseline policies, for some workloads, they perform really well. But for some of the workload, it's really bad. They perform really poorly. And on average, you get 41.1% lower performance. So these policies are not really good for all different workloads. And this is because these policies just consider like statically tuned characteristics, and they just expect it's always going to work. But that's not really true. And now if we go for lack of adaptivity to device types or configurations, for example, if you change the underlying devices, so if you go for a new storage device, then some of these policies, again, don't really perform well because they are designed for specific devices as well. So for example, if we take the similar results we had for workloads for HSS configuration 1, over here, we compare it with the slow only policy. So this policy, there's nothing smart about it. It places everything in the slow storage. And then if we see in this kind of hybrid storage configuration, all these smart policies like this heuristically designed, like CDE, or also like using machine learning, like this RNN policies, they are even performing worse than a slow only policy, which means these policies are not really designed for these hybrid storage configuration. However, if we go for a hybrid storage configuration for which these policies have been designed, then we see like these workloads are performing really well and they give like really high benefits, which is because these policies are not designed for all the different configurations. And we conclude that there is high diversity of storage devices, and we can't really have a single policy which will work for all the different scenarios. And then there's also lack of extensibility. So for example, if you added a new device instead of a dual hybrid storage system, and now we have a tri-hybrid system, and then the designer needs to kind of design the policy again, because you need to, if you're using a static policy, you need to set the thresholds again, when the data should be in the fast storage, when the data should be in the mid storage, or it should be in the slow storage. So you need to design it again, everything. And then you need to handle the scenarios of like when the data should be evicted, when the data should be promoted from one device to another. So that's why there's significant effort which you have to put always, like a designer had to redesign these policies. So it's not really good. So that's why our goal in this work was to design a data placement policy, which provides adaptivity, which can continuously learn if you have a different hardware or if you're using a different workload, and also provides easy extensibility. So in case you change the hardware, like you add more devices, then you don't need to redesign the policy from scratch. That's why in this work, we propose Sibyl, which formulates data placement as a hybrid storage, in hybrid storage system as a reinforcement learning problem. So I'll go into the formulation of reinforcement learning, and it's quite similar to what Rahul explained before. So you already should be familiar with it. So in reinforcement learning, we have an agent and an environment. So the agent is always observing the state of the environment. And based on the state, the agent performs an action. And then the environment gives a reward to the agent, which is kind of a feedback to the agent how good or bad the action was. And based on this feedback, the agent will change its action and learn a new policy. So in the end, the agent wants to learn to take an action given a state, which will give the maximum reward. So in the end, that becomes the policy of the agent. And if we look into the formulation, so over here we have an agent, which will be Sibyl in our case, which is a data placement agent. We have an environment, which is hybrid storage system. And then for each request over here, which becomes the state. And we give some sort of features, for example, what's the current features of the request, what sort of features from the hardware as well. So the agent is aware of both the workloads and also what's underneath hardware as well. And then the agent performs an action. And in our case, the action is where to store the data. Should it go in the faster device, or it should be in the slower one? And then the agent receives a reward. And in our case, we define the reward in terms of request latency, because it's able to encapsulate a lot of different aspects. And I'll go into each of these one by one. So first, let's look into the state. We use limited number of state features because we wanted to reduce the implementation overhead. So we perform like feature selection to only select the important state, which are really important to perform the data placement decision. And then, and also we observe that the RL agent is really more sensitive to the reward rather than the state feature. So it doesn't really help if you keep on adding this, like more characteristics or more different kind of features as well. And in the end, we have a 6-dimensional vector of state features. Which is, for example, the size of request, the type of request, or and the hotness of a page, and these kind of things. And then we also quantize the state representation into bins, so to reduce the state overhead. So I'll come back to these things when we talk about like what sort of a reinforcement learning agent we are using. And then for the reward, as I mentioned, the reward is kind of a feedback for the agent. So it's kind of defines the objective, what you want to achieve. So it could be request latency, or it could be energy, it could be all different things what you want to do. And in the end, like we formulate reward as a request latency because it's able to encapsulate different aspects. For example, the internal state of the device. For example, if you have, there's a garbage collection going on, so the latency will be higher. So indirectly, the agent will be aware what's happening is the latency is higher. So it will be able to learn these things. And also it encapsulates like throughput and also the evictions as well. So because if something is being evicted, then the latency will be higher. So indirectly, it's able to capture these things. So that's why we gave as an example of using of designing a data placement agent using a request latency, but in the end, you can always have like different objective what you are trying to achieve. And then we provide more details about these reward features and how we really create the reward in our paper. And if I look into the action, and as I mentioned before, the action is where we want to place the data. It should it be in the faster storage or in the slower storage? So that's the action. And this kind of action help us to provide like easy extensibility. So in case if you extend your devices to more devices, like a tri-hybrid system, you just give a new action, that's it. And then the agent will itself find a new policy. So you're not redesigning anything at all. And also this kind of action helps Sibyl to proactively learn whether to promote a page or to evict a page, because it will eventually know whether if the data will be eventually evicted from the faster storage, then it will inherently kind of try to learn that it shouldn't place that data into the faster storage. So there are like a lot of implicit things which happen based on how you define your state and action and reward. Do you have any doubts until now, or? Okay, cool. So I'll keep going. So I'll go into the overview of Sibyl. So as I mentioned, like Sibyl, we implement Sibyl in the host OS, and we do everything as on the real system. And in Sibyl, we have two different threads. If I talk about the execution model of Sibyl, so first there's a RL decision thread, which whenever there's a new request, the decision thread decide where to serve this request. But also in RL, you also want to update your policy. like based on like maybe the policy which you had was not performing really good. So you need to somehow update this policy. So we have another thread, which is called the RL training thread, which is working in the background. And what we do is we keep collecting this information of state, reward, and action. And we keep on providing this information to the training thread in the background. And what this thread is doing, it keeps on learning whether it's performing the right action or how the policy is, and it keeps on updating its policy. And every now and then we do this kind of evaluation when we should update the policy between the RL training thread and RL decision thread. We just transfer the new policy from between these different threads. And these threads are working asynchronously, which helps us, like, for example, if you have a request, then you're not getting kind of stopped by this training, which is happening in the background. So everything can work asynchronously. So there's no sort of delay, and you're not really limited by this training overhead, which is happening. And now I will go into the implementation of each thread. So over here, we have two different phases. So one is RL training thread, as I mentioned, and at the bottom is the RL decision thread. And let's discuss the decision thread first, where Sibyl has to just decide where the data should be placed, whether it should be in the fast or the slow. And in this thread, additionally, also like in addition to the decision, it's also storing its information into an experience buffer. So what happens is, like, when you get a new request, there will be an observation vector, which is the state information, like I mentioned, different features. In our case, which could be like the request, size of the request, the type of request, the hotness of page, these it's kind of like the metadata which you provide. And then based on this, we have an RL agent, which is based on a feed-forward network. So it's a really simple network. So it's a bit different than what Rahul's work with Pythia was, which was using a tabular approach. So I wouldn't go like really deep into those things, which is like a complete different lecture on reinforcement learning approaches. But if I give a brief overview, so in a tabular approaches, you have all the state action, you create a table of all the state and action, and you put all the values into a table. But when you go to like some sort of situation, like in this case, where you have a data placement, there could be millions of different pages. So if you have to keep store a table for all different state action possibilities, the overhead would be super high. That's why what we do is for these bigger problems, we kind of use these neural networks, which kind of approximates the value of the table. So in the end, this neural network should provide you, given a state, an action, or an action, what would be the Q value? Q value is kind of the quality of your action, like just to abstract things. So in the end, the neural network does that, and it's helps with like this overhead of to overcome the overhead which we'll have if we keep a table of all the different actions of like millions of pages. And so that's why we use it's called a deep reinforcement learning. So we use that approach, and it's not really deep, like the network is quite simple here. And we just use like a simple feed forward network. And in the end, like, and then once you have this observation vector, then Sibyl has to decide where you should place the data. And once you perform this decision, in the background, we are also taking, as I mentioned before, we are also collecting information about the state, action, and reward into an experience buffer. And this buffer is nothing but a space which we use for training the RL training thread, which happens asynchronously in the background. So for the training of the network, what we do, we have all the information which is stored in the experience buffer, and we keep on training this new policy in the background from this new data which has been collected into the experience buffer. And every now and then we update the weights from our training thread into the decision thread. So these two threads are happening asynchronously, and we just transfer the weights. So there's no separate training thread which happens, training step which happens for this RL decision thread itself. We just transfer the weights. And that's how we are able to guarantee that there wouldn't be any issues in terms of like making a data placement decision. Everything will happen in a timely manner. So that's a bit of overview of how these different threads work. So like I mentioned, I'll give a brief overview of how this network looks like. So there's just like a simple, like a 2 layers of feed-forward network. We just have two hidden layers, and what we give in the input, we are providing the observation vector, which is the size of the request, and based on this, on the state, our network has to predict what will be the Q values for each of the actions. So in our case, for example, we have two actions, so we have just two neurons at the end, and then it provides us with like the possible probability of different actions. And based on like the highest probability, we select which should be the next action. So that's what like how the network looks like, and it's quite simple. It's not really big as well in the end. And then we use this this network in our in Sibyl instead of having a tabular approach. So now I will go into the results. Before I do that, anyone has any questions, or please feel free to ask any questions. Okay, cool. So now I'll go into the key results. As I mentioned, we perform real system evaluations for both dual hybrid and tri-hybrid systems. So here you can see our evaluation setup that consists of multiple different devices. So over here we show like 3 devices, and we implement everything in the host storage management layer of AMD Ryzen CPU. We evaluate 2 different configurations. So first is a cost-oriented HSS configuration, which is we have a high-end SSD, which is connected to a low-end SSD. So the latency difference between these 2 devices is quite significant. And then we have a performance-oriented hybrid storage configuration where the latency difference is not that significant between the 2 devices. And then we use 18 different workloads from MSR Cambridge work suite, and also a file bench suite. And we have also 4 state-of-the-art data placement policies. So we have 2 different heuristic-based policies, which are called CDE and HPS. And then we also compare our approach to state-of-the-art learning-based policy like archive-based and RNN HSS. And then if we look into the performance analysis, for the cost-oriented hybrid storage configuration. So on the x-axis, we have the different workloads. And again, on the y-axis is is the request latency. So lower the better. And we are comparing always to Oracle, which is impractical, and we can't really achieve it in the end. That's the best we would like to do, but we can't. It's impractical. So if we compare Sibyl with this Oracle, we consistently outperform all the baseline policies for all the workloads in this configuration. And then if we go for a performance-oriented hybrid storage configuration, where the difference between the latency is kind of similar. And in that case, again, we are able to provide like high benefits, which is 26.6% improvement by dynamically adapting our policies to different data placement scenarios, for example, the change in configuration, the change in workload. But then we also see in 2 workloads, Sibyl is providing a bit lower performance. And we try to analyze these workloads, and these workloads are a bit like write intensive. And in this configuration, when you have really the performance gap between the 2 different devices is not that much. It's better to retrain the network quite frequently. So you transfer the weights like more frequently. So you update the policy more frequently. And then you can even provide better performance in these kind of workloads. So we provide these results in the paper as well. But in the end, still, Sibyl achieve 80% of the performance of an Oracle policy that has the complete knowledge of future excess patterns. So that's compared to other data placement techniques, it's quite good. And then, as I mentioned, for us, one important concern was also extending our policies. So the designer doesn't have to spend too much time on building new policies every time. So that's why we wanted to try a tri-hybrid system, where instead of just having 2 devices, we also have another device. And then there's like 3 different scenarios. For example, there's a high-end SSD, which is the latency is really low, so the access is quite fast. Then there's a mid SSD, which has a latency between this low-end SSD, which is really slow. And then if you want to extend Sibyl for a new device, so what you have to do is you just add a new action, for which would be like, for example, we already had the action for high end and the mid end. You just add a new action, which should be action number 3, which will be stored data in the low end. And then we also, in our state feature, we also provide the remaining capacity. So we also added the remaining capacity of the new device in the feature, and that's it. And Sibyl itself will find the new data policy. You don't need to rewrite anything about like different scenarios and everything. It will dynamically come up with the new policy. So over here, we have the results for of using this tri-hybrid system with state-of-the-art data placement policy, which is a heuristic-based policy. It's kind of an extended version of CDE policy. So we had to do a lot of significant effort to extend this policy because it was heuristic-based. So we had to handle all the different scenarios, what could happen in case of eviction or promotion, these kind of things. So over here as well, again, on the x-axis, you have all the different workloads, and on the y-axis is the request latency. So the lower, the better. And we compared to Sibyl. And again, we observed like Sibyl provides like really high benefits in all the different workloads. And on average, we are able to outperform this state-of-the-art data placement policy for tri-hybrid system by 48.2% on a real tri-hybrid system. And in the end, like Sibyl reduces the system architect's burden by providing ease of extensibility, which is really good for designing like future systems when you have not even three hybrid storage configuration. You could have like 5 or 100 as well. So it's really good for like these future systems. And all of these Sibyl's overhead.
How close the performance to the Oracle in the tri-hybrid system?
Yeah, so it's a good question. We like the Oracle was always a problem for us because the Oracle could be designed in many different ways. So in the end, we didn't really settle on an Oracle for a tri-hybrid system. So we don't really have any Oracle here, and there's no, I wouldn't say like a set standard of how it should be. So we don't really have any Oracle. So we only compare to the heuristic policy here. But yeah.
Per bound could be always.
Right. Yeah, we don't, I think we don't have the results here, right? Yeah, we don't have it. Right.
Just to see. I mean, it's of course an unrealizable upper.
Right.
Is it upper bound the performance improvement you can get?
Right, that's true. That's true. It's a good point. Any other questions? Yeah.
So we have a training thread like laying in the background. I'm just curious, how much computational overhead does it have?
Overhead for, sorry?
So how much overhead for the computational resources does it take for the training set?
Oh, right.
Training thread to be like kept there?
Yeah, actually, I was going to come to that part, so maybe, and it's a bit different than like the traditional training of when you have this supervised learning. It's a bit different. It's not like you have kind of separate stages, but you kind of do it in the background. It happens on the fly, like the training and the inference, like if you want to put it this way. So like the reinforcement learning is a bit different in that way, but I'll come to the overhead now. Anyone else? Okay, cool. So, okay, let's talk about the overhead. So first we talk about the overhead in terms of the storage cost. So it's not really high overhead because we only need an experienced buffer, a simple network, which was just two hidden layers with few neurons. Same for the inference network and the training network. So in the end, we just have like 124.4 kilobytes. So it's not super high. And then we have an additional overhead for 40-bit metadata, which is for per page, because we provide these state features, as I mentioned, like size of request or like the hotness of a page or different feature. It could be a lot of different ways you want to describe your state features. So our overhead is 40 bits for that. And then the inference latency is 10 nanoseconds. So the inference latency to perform a data placement decision is 10 nanoseconds, which is actually quite low, even compared to all the state-of-the-art SSDs as well, because their read latency, for example, a Samsung Z9, which is state-of-the-art storage device, it takes 3 microseconds. So it's quite low in terms of the inference latency. And if you talk about the training latency is 2 microseconds. And in the end, like I mentioned, everything is happening asynchronously and training is happening in the background. So the inference and training are not really affecting each other. And so in the end, like we have a small area overhead, we have a small inference overhead. And since we are doing everything asynchronously in the background, so it satisfies the prediction latency as well. So in the end, the overhead is not that much, and we do it on the real system, and we show all the results as well that we are able to perform these effectively.
So where is the inference happening exactly?
So inference in the sense, I mean, everything is happening on the CPU, like if you mean the hardware. Yeah, everything on the CPU. Yeah, everything on the CPU. Because no, I don't even think it makes sense to have a specialized accelerator, at least for the reinforcement learning, because it's kind of a sequential process. So you have like a state, then you take an action, then you give the reward. So it wouldn't, in my opinion, if you just have a single environment, then it doesn't really make sense to have a specialized accelerator, at least for inference. Maybe for training, you can do it for the training thread, because in the end, you just have the data, which is in the experience buffer, and you're just training everything on the new policy. So for that part, it makes sense. Maybe if you have like different environments, like a different parallel environment, like a distributed system where you have like a lot of different environments which are running in parallel, then maybe you can have like instead of single inference, there will be multiple inferences which will be happening, multiple data placement decisions. Then it could make sense as well, I think. But at the moment, like when we evaluated, we were trying to offload our computation to GPU. Actually, the overhead was higher because then you have this off-chip data transfer happening between the CPU and GPU, and then you get the decision back. So it was not really helping in the end.
We were trying to offload the
Right. Yeah, so it didn't really help us in that case.
The inference is still going through the neural net.
Yeah, still, but it's yeah, exactly. So it's a really small, like there were like 30 layers, 30 neurons in the first layer and 20 in the next. So there was not much actually in the end. Yeah, thanks. Yes.
Do you have to train continuously, or like when do you pay for this training?
Right. So this training so that's a good question. So once our experience buffer is full, and we also have like a experience buffer of like 1,000 entries, which it's also kind of a hyperparameter which we set. So once the experience buffer is full, then we train it. So after every 1,000 requests, something like this. So it's not that high as well in the end. So I mean, there was no reason to choose 1,000. We just chose it based on like we did a empirical analysis, and we came up with like maybe like the 1,000 requests are like good enough, and then we don't really interfere with the training and inference in that case. So it could be a different as well.
Is this training latency the same as
No, it's not. It's after 1,000 requests as well. So it's yeah.
These numbers are quite interesting. You cannot have these numbers in multiple.
Right.
Prefetching very quickly at the nanosecond latencies. You cannot afford microseconds, but here the application is completely different.
Right.
You can afford the microsecond latency for training.
Right.
And as a result, you can do it on a completely real system, right? The evaluation is on a real system also. You don't need to modify anything in the hardware.
Right. And to make sure that we satisfy the latency, that's why we did it like asynchronously, these inference and training. If we didn't do that, it could have been a problem as well. Like when you have to make a data placement decision, at least in hybrid storage devices, it's still better because you can still afford a bit of higher latency. But if you go to hybrid main memory, then it will become an issue there. So this is already like a nice direction to explore. If you would like to explore something, you can just take the code which is there on our GitHub and try on hybrid main memories. And there will be more new constraints as well there.
Would it be an issue if, say, there are so many requests that the training thread is still training the next model, and then the experience buffer is full? Is this going to be an issue or no?
Like you mean if there are like multiple requests coming at the same time?
Yeah. So you said that after the experience buffer gets full, it will be sent to the training thread to be trained, and then. In the meantime, if the experience buffer is full again,
Right.
because there are many requests, what will happen? Is this going to be an issue, or it's just going to be queued or something?
Yeah, it's a really good question, because at the moment we just queued everything, so we didn't really we didn't let it overflow, kind of. And actually, it's a really good concern, because we were thinking of having like a a meta buffer in the background. So in the end, you duplicate the buffer. So one buffer is just used for training. And once it's full, then you start filling the other buffer. So it's like a ping pong buffer. So we were trying to implement this as well. So in the end, we didn't really do that because we just assume that we can queue the request. And also like another thing is we didn't really do like multiple requests coming at the same time. So we always kind of queued. So this scenario would be quite valid when you have like a lot of different requests coming at the same time and you need to serve somehow, then you have to handle these cases. So that's also quite interesting to do that. It's a really good question. Yeah, for sure. There's a lot to be done. So I'll go a bit further as well. So yeah, so we have like many more results in the paper in terms of throughput as well. We also provide evaluation of unseen workloads where we don't really train the policies beforehand, and it doesn't really have the notion of like what sort of workload it would be. We also try a mixed workload where you have like different characteristics. And then we also give evaluation in terms of like how to choose different features. So we perform a feature selection. Like I mentioned, there could be a lot of different state features which you can provide. And then we also do like explainability analysis, which is like really important when you are going for these machine learning based, especially like with neural networks. You need to provide some sort of intuition why your model is behaving in such a way, which is, I think it's a really good research direction itself as well to provide explainability to all the decisions, because often what happens is we just take like a big neural network and it performs some action and we don't really have an intuition why it's doing that. So it's good if you can do that, like explain the result. And in our work, we tried to explain based on the workload characteristics. So we knew like certain workloads, how they're performing, whether they're read intensive, write intensive, or like how hot or cold pages they have. So we tried to give some sort of intuition based on that, but there could be different ways to do like explainability analysis. So it would be a good direction as well when you apply machine learning for your own problem or some other domain as well. It's a good direction itself. So yeah, so we have like many more results in the paper. So this is the title of the paper, and we have it on archive, and also the code, like I mentioned before, it's on GitHub. So you're free to try, you can play around with it. You can also try with a different scenario, different kind of application as well. And I will be happy to help with those things. And if you have any more questions, or if you want to understand those things, please feel free to write to me. So yeah, do you have any more questions? Otherwise, I'll conclude my talk.
I have a question.
Yeah.
First of all, I have a comment. The explainability analysis is actually really important.
Yeah.
It's good to do that whenever you can. Otherwise, you're just throwing machine learning at the problem and doing something. And a lot of people are doing that these days. It's good to try to understand what is going on, what the machine learning is bringing to the table, right?
Right.
Second thing is, this is actually all of these are actually great topics to build on in terms of research. They're also very fundamental, as you can see, right? These are tackling really fundamental issues in computer architecture. So if you're interested in building, certainly contact Rahul or Gagan or Hayu, who will be presenting next after them. I will ask a question now, which is these systems that you investigate, how much do they cost?
How much do they cost?
Like if someone wants to do this experiment in their, I don't know, garage, how much do they need to pay to get the tri-hybrid system?
I think it was not that expensive because we did like a desktop system. In the end, it was like you can easily get like it was a cheap CPU, and we tried like the drives would be, we were using like a old hard drive as well there, which would be like few hundred. And the other, like the faster one was the most expensive, the faster storage, which wouldn't be like more than 1,000. So I think easily you can try like at most 1,000 or something. And everything is in the OS.
Like an underestimate, but
yeah, you paid for it. So
I guess if you don't pay, you don't know.
Yeah, exactly. Yeah, but everything is implemented in the OS, so you can try like implementing these things on the OS, like at least Sibyl itself. So you should be able to do those things. So yeah, the cost part, please refer to Onur for that. So I'll conclude my talk. So we introduced Sibyl, which is the first reinforcement learning-based data placement in hybrid storage systems, which provides adaptivity, easy extensibility, and also ease of design and implementation. We extensively evaluate Sibyl on real system using many different workloads and many different configurations. And we show like it extensively performs well, and it gives higher performance in both dual hybrid and tri-hybrid systems. And in the end, Sibyl is able to achieve 80% performance of an Oracle, which is impractical at a design overhead of only 124.4 kilobytes. So thank you. Yeah, thank you.
No other questions to Gaga while Hayu is getting set up? Okay, thanks, Gaga. I think next up it's Hayu. Hayu is also a postdoc in my group, and she's going to talk about something completely different, but it's related to what we have covered, acceleration of genome analysis. And she's going to talk about some ideas on accelerating genome analysis by using in-memory computation and reducing data movements, and also reducing useless computation and integrating multiple steps of the genome analysis pipeline. And we have enough time, so feel free to ask questions.
Can you hear me? Can you hear me? Is it good? Is it good now? Yeah. Cool. Yeah. Hey, I'm Hayu, and I'm gonna introduce our paper, GenPIP, which is in-memory acceleration of genome analysis by tight integration of Basecalling and remapping. And I go have an overview of this paper, and as far as we know, that genome analysis enables us to determine the order of a DNA sequence in the organism's genome. And it plays an important role in the personalized medicine, outbreak tracing, understanding the evolution, and so on. And modern genome sequencing machines extract the smaller randomized fragments from the original DNA sequence, which is known as reads. And this is a picture of the ONT sequencing device, which is called Oxford Nanopore sequencing. And device is a widely used sequencing technology because it's portable sequencing. It provides portable sequencing devices, and it has high throughput. Also, it's very cheap. And however, there are two main limitations in the current genome analysis pipeline. First of all, there's multiple steps in the genome analysis. And the first problem is that there's large data movement between multiple steps, and there's a lot of wasted computation done on data that is later discovered to be useless. So let's have an overview of the GenPIP. GenPIP is a fast and energy efficient in-memory acceleration of the genome analysis pipeline via tight integration of the genome analysis steps. And GenPIP has two key techniques. The first one is a chunk-based pipeline, which provides fine-grained collaboration of genome analysis steps. And the second one is early rejection technique, which timely stops the execution on useless data by predicting which reads will not be useful. And GenPIP performs state-of-the-art software and hardware solutions using CPU, GPU, and the optimistic beam. Let's first have a background, look at the background of our motivation. First of all, we have the genome sequencing devices, and after sequencing the genome, then we got the raw signals, and we store the raw signals in the storage. After that, we read out to do the first step, which we known as Basecalling. In the Basecalling, we usually use the deep neural networks and translate the raw signals to the ACGT, the character basis as we know.
Here is an example that we cut the raw signals into the chunks, and we base call the chunks and to the chunk of bases. And after we base calling all of the chunks, and we assemble them into a read. After we finish all of the base calling, we store the reads in the storage. And then we continue with the next step, which is called the read quality control. In the read quality control, as you can see, when we have this kind of reads, the green one represents that it has a high quality for the bases. And the red one represents that we have a low quality for the base. And through the read quality control, we calculate the quality score of each read. And if it's low quality the read, then we discard it. And if it's high quality read, then we store it in this storage. Then we continue for the next step, which is known as read mapping. In the read mapping, we compare each read to the reference genome. And if the reads cannot be mapped to the reference genome, then we discard it. If the read can be mapped to the reference genome, then we store the mapping results to the storage. So this is a whole like a genome analysis pipeline. And as you can see, there are two limitations. The first one is the large data movement. Here is an example that we use the human data set to do the analysis. First of all, we have raw signals, which is very big. And then we do the base calling, then we transfer the reads to the read quality control, and then we store and transfer the high quality reads to do the read mapping. And last, we only have the 300 something like mapped reads to the store in the storage. So here there's a large data movement between each genome analysis step. And the second one is we found that there's a lot of wasted computation. And we also use the same like human data set to give an example here. And after base calling, we have like all of the reads, but after the read quality control, we filled out a lot of low quality reads. It's 20% here. And we only send the 80% of high quality reads to the read mapping. After read mapping, we only have like 70% mapped reads, and it's like 70% is useful, and other nearly like 30% is unuseful reads. So there's a considerable amount of computation on useless data due to the low quality reads and unmapped reads. But these reads are already like a base called and or through the read quality control and read mapping. So let's have a look at the state of works. There are many like non-volatile memory-based PIM to accelerate the base calling step or the read mapping step. Since the base calling step is dominant by the product operation, then we usually use the like NVM-based PIM for the dot product operation to accelerating the base calling, and then to apply for the other operations to accelerate to implement the whole thing, and then we can accelerate the base calling in the memory. Also, the same for the read mapping. We have NVM-based PIM for the search operation and addition operation, and we can implement other operations using the peripheral circuits, and we support the read mapping acceleration inside the memory. And there are many works, not only these two, but there are many works to do the acceleration in memory acceleration for either the base calling or the read mapping, but they don't do the acceleration of the whole pipeline. So this acceleration, they can reduce the data movement in a single genome analysis step, and but it exacerbates the data movement overhead between analysis steps. And we found that there's no prior work tackles the problem of data movement between analysis steps and reduce the useless computation. So we found that there are many opportunities for us. So the goal of our work is to efficiently accelerate the entire genome analysis pipeline while minimizing the data movement and useless computation. And we perform a study to quantify the potential performance benefits, and these results are normalized to the performance of GPU. First of all, we perform analysis of NVM-based PIM accelerators for separate base calling and read mapping steps. And as you can see, it achieves the 2.7 times speed up compared with the genome analysis in the CPU. And second, we consider there's no data movement between the accelerators of analysis steps. Then it can achieve 6.1 times speed up compared with GPU. And third, we consider there's no data movement and no useless reads, which is the ideal case. And it can achieve up to 9 times of speed up compared to GPU. So do you have any question for the background and motivation? Okay, and I continue with introduction to our GenPIP. GenPIP is the first holistic in-memory accelerator for the genome analysis pipeline, including the base calling, read quality control, and read mapping steps. And GenPIP has 2 key techniques: trunk-based pipeline and early rejection. Let's first have a look at the trunk-based pipeline, which enables the fine-grained pipelining of genome analysis steps and processes reads at the trunk granularity. Trunk granularity is a subsequence of the read, which usually to be like a 300 bases. And our trunk-based pipeline increases the parallelism by overlapping the execution of different steps at trunk granularity. And trunk-based pipeline also reduces the intermediate data by computing on data as soon as data is generated. And trunk-based pipeline also provides opportunities for the early rejection by analyzing a read at the trunk granularity. And here is we use an example of a read, which consists of 4 chunks, C1 to C4, to explain. For the conventional pipeline, we base call the 4 chunks one by one. And after we finishing all of the base calling, then we assemble the chunks into a read. And we do the quality control and the read mapping on the read. And in our trunk-based pipeline, we base call the trunk. Then at the same time, we base call another trunk and do the quality control and the partial computation of the read mapping on the first chunk. And we do the base calling, quality control, and the read mapping at the same time in parallel. And after that, we assemble them to do the rest of the computation on the read. And as you can see, there are some saved cycles. Okay, next I would introduce the second technique of GenPIP, which is early rejection. Early rejection stops the execution on the useless reads as early as possible by using a smaller number of chunks to predict the usefulness of a read. And early rejection predict and eliminate low quality and unmet reads from the genome analysis pipeline as early as possible. First of all, we base call a small number of chunks. After that, we check the average score of these chunks. If it fails, then we stop that whole analysis for the read. And if it passes, then we base call more chunks. And then we map the base call chunks so far to the reference genome to check the mapping score. If it fails, then we stop analysis. If it passes, then we base call the remaining chunks. And then we execute the remaining computation in the remapping. So as you can see, there are 2 parts of early rejection. Early rejection based on the trunk quality scores, and which predict the low quality reads by using several base called chunks. And the next one is like early rejection based on the trunk mapping scores, which predict the unmapped reads using the trunk mapping scores. We have a lot of details of this and in the paper to how to choose the sampled chunks for the early rejection based on the quality scores and early rejection on the mapping scores. And it's worth to mention that our like trunk-based pipeline and early rejection can also be applied on the different systems such as CPU, GPU, and PIM. And we implemented this in the PIM since PIM is more efficient to reduce the data movement between genome analysis steps. And we also applied the CP and ER on CPU, GPU baselines and observe speed up and energy savings. Okay, let's have a look at the GenPIP implementation and the evaluation. First of all, GenPIP has 3 modules: the Basecalling module and the read mapping module and GenPIP controller. And at the beginning, we read the raw signals from the sequencing machine and store it in the IEDM buffer in the GenPIP controller and send the signal trunks to the Basecalling module. Here we have the in-memory Basecalling. It's worth to mention that we don't focus on the acceleration of the Basecalling step or the read mapping step. We can there are many accelerators for these steps, and we can our architecture is orthogonal to these accelerators. So after Basecalling, we obtained the Basecalling scores, and we designed a unit called the PIM trunk quality score calculation to calculate the trunk quality score as soon as possible when we have the Basecalling trunks. And then we send the trunk quality score to the average calculator, which can calculate the quality score of a trunk, and then at the same time send the Basecalling trunk to the buffer. And after that, we send the trunk to the read mapping module. In the read mapping module, we do the read mapping in memory, and after that, we send the read mapping results to the storage. Here, I want to introduce the how to integrate the early rejection in the GenPIP. And to integrate in early rejection, we need the quality scores from the average calculator. And then we have an early rejection controller to compare the quality scores we have with the threshold. If there is early rejection, then based on the quality scores, then we send the early rejection signal to the Basecalling module and to terminate the execution of the Basecalling on the current read. And if we also obtain the trunk mapping scores from the read mapping controller, and to compare the trunk mapping scores to the threshold. If there is a early rejection based on the trunk mapping score, then we send the early rejection signals to both read mapping, Basecalling module and read mapping module to terminate the execution on the current reads. And here are the several units that we design, and can check more details in our paper. And by tightly integrating the genome analysis steps, and as you can see, we can reduce the data movement and eliminates useless computation. And before I go to the evaluation, do you have any questions about the mechanisms? Okay, then I go to the evaluation. We evaluate our GenPIP use the performance and the area and the power analysis using the several simulators. And then we choose 3 baselines, actually more in the paper. We use 3 baselines here: CPU, GPU, and the optimistic integration of 2 PIM accelerators. This optimistic integration of 2 PIM accelerators, we consider that there's no area overhead, area limitations for the accelerators, and also the power limits. And also assume there's no data movement between the steps, and there's enough space to store the intermediate data. And we use 2 data sets, which is commonly used for the genome analysis. One is E. coli and one is human data set. And here is the key results of our performance. And as you can see, that GenPIP provides 41.6 times speed up of CPU and 8.4 speed up of GPU and 1.4 speed up of the optimistic PIM integration. And both in our paper, we showed more results to say that like both CP and ER are critical to the speed up. And here's the result for the energy efficiency. And GenPIP provides 32.8 times energy saving over CPU and 20.2 times energy saving compared to GPU and 1.37 times energy saving compared over the optimistic PIM integration. And early rejection is especially critical to the energy efficiency according to our experimental results. And there are more details in the paper. You can access the paper on arXiv, and including details of CP and ER, detailed GenPIP implementation, and GenPIP controller early rejection implementation, and in-memory seeding accelerator, and also more results of applying CP and ER in CPU and GPU, and sensitivity analysis on the number of sample chunks is for ER, and area and power analysis. Before I conclude the talk, do you have any questions? Yeah.
So is the performance boost based on the current fast file format for the ONT data?
Is
the performance boost currently measured performance boost based on processing the fast file format of ONT data?
Yes.
Have you ever compared it with using the result using slow5, which is say a newly published ONT data format this year?
No, we don't. It was like completed like last year, so we haven't done it yet. Yeah.
Then I'm kind of curious how much time is spent on processing the raw signals from the sequencing machine, or the time spent on the I/O instead of computing. Because as far as I know, the I/O for ONT is quite slow.
Oh yeah.
Yeah.
You can like use multiple devices to sequencing the genome, and after we sequence the genome, there are many. We only consider after there are many like raw signals upload to the for multiple analysis. As you can choose different parameters to analyze the raw signal for different purposes. Yeah, we don't consider like a real-time analysis, like analysis of the when the genome is like sequenced by the ONT devices. Yeah. So are you asking like the throughput of the machine and the throughput of the genome analysis, the differences between these two? Thank you. Okay, no more questions, then conclude our talk. So the problem we target in the paper is that the genome analysis pipeline has large data movement between the genome analysis steps, and there is a significant amount of wasted computation on useless data. So our goal is to tightly integrate the genome analysis steps to reduce the data movement between the steps and eliminate the computation on the useless data. So we propose GenPIP, which is the first in-memory genome analysis accelerator that tightly integrate the genome analysis steps. And GenPIP has two key techniques: a trunk-based pipeline and a new early rejection technique. And GenPIP outperforms the state-of-the-art software and hardware solutions using CPU, GPU, and optimistic PIM by 41.6 times and 8.4 times and 1.4 times respectively. And that's all for my talk. And thank you for listening.
Any other questions? I think just clarify. I believe you do this analysis after the signals are stored in the
Yes.
storage.
Yes, yes.
You can't really do the analysis on the device, right? It's limited by the communication from the device
Yeah.
to the storage.
Yeah, yeah.
But you could potentially do it on the device, everything. But that's yeah. Yeah, there are a lot of issues with device integration, but that's okay. No other questions? Okay, I'll just make a comment. It's important to one of the things this work does is it tries to get rid of useless computation as early as possible, right? You don't even want to base call some signals if you think that that read is not going to be used downstream in the analysis. And I think well, we need such methods to eliminate data as much as possible, so that we don't overwhelm the analysis engines that come downstream going forward. So there's a lot of things to be done in that direction, I think. Okay, I think we're done today and we're on time. There are no questions. I will see you next week.